Sir, good afternoon, sir.
Good afternoon.
This is Dr. Venkateshri, sir. So it is
I think your face is not visual, but it's okay. Camera adjustment. Now I can see. Thank you.
Good afternoon, sir.
Good afternoon.
Sir, shall we start?
Yeah.
Yeah. We should start. I am ready.
Yes, madam. You can start.
Yes, sir. So now the session will be both on Zoom and also YouTube, sir.
Okay.
So more than 200 participants joined, so we cannot accommodate all of them in Zoom.
Yes.
So we shared it live streaming through YouTube. So all of them can watch this live video. So good afternoon, one and all. This is Josna Devi Bodapati, Assistant Professor, Department of CSE, Vignan Stream to be University. Being the coordinator of this event, I am very much excited to see large number of participants joining this meeting. Respected participants, faculty colleagues, and my dear students, it gives me immense pleasure in inviting you all to this webinar on evolution of artificial neural network architectures from learning to deep learning. A series of webinars are scheduled by the Department of CSE to make the students and faculty well acquainted with recent developments in research. As part of this initiative, we are here with this first webinar on evolution of ANN architectures. For this webinar, we have with us Professor B. Yegana Narayana, an eminent researcher who have more than 5 decades of research experience in the area of speech and signal processing. In this webinar, he will share his perspectives on the evolution of various neural network architectures. Along with that, he will also discuss the journey of neural networks from learning to deep learning. Over the past few decades, we have been witnessing the success of machine learning applications in our day-to-day lives, starting from speech recognition systems, weather forecasting, fraud detection, recommendation systems, and many more. So inspired by biological neurons in the year 1940, artificial neural networks were introduced. Since then, ANN has become an active research area, and there were many evolutions of these neural network architectures. In the year 2006, deep neural networks were introduced by Intel. Today, deep learning is transforming every industry from healthcare to financial services. The interest in these deep learning models has escalated as they enable computers to perform tasks that were previously believed to be impossible. Deep learning is the latest trend in machine learning, which produces state-of-the-art results in various applications like speech translation to driverless cars. The core of deep learning is constructing and training deep models to solve real-world problems. In this webinar, we aim to discuss the evolution of various ANN architectures along with a detailed discussion on the changes that were introduced in the learning of these models. Now, I request Dr. D. Venkateshri, Head Department of CSE, to speak few words on this occasion.
Good afternoon, everybody. It's a warm welcome to our teacher, Professor B. Yegana Narayana garu, was INSA senior scientist, IIIT Hyderabad. So I am very fortunate enough to see Professor Yegana Narayana garu in 1991 to 1997. So I have been associated with the Department of Computer Science and Engineering. So I could, though I was not associated with the area of research wherein the Professor Yegana Narayana garu involved, and I am completely working in the area of networks. But we have been hearing, great things about the laboratory, especially on the pattern recognition. So I'm very proud to be part of this webinar. So when we requested Professor Yegana Narayana sir, so he has kindly accepted and accepted to deliver a webinar on evolution of artificial neural network architectures from learning to deep learning. So we are very much grateful to you, sir. So we can start the webinar, sir.
Okay. Thank you, Dr. Venkateshri garu, and Dr. Joseph. So I was asked by your university to give a talk on whatever are the current trends, but what I decided was to talk about how we reached to this point where we are talking about trends at this time. That is the goal of this talk, because many of the recent trends, I think most of you or some of you who are active in this field may be more familiar than me and more sort of expert than me in this. But what we need to know is we landed up to this point, you know, and why most important thing is for us to understand, all of us to understand that, especially youngsters, what is the meaning of these various terms that are being used. You see, very unfortunately, in my opinion, the terms are quite misleading. If you ask any two people about the meaning of these terms, I don't think any two will agree on even 80% of it, even 10%, 20% of it. You see, and that is the situation we are in. And because although I have not directly worked on applications of this, although I did through my research scholars, but the point here is I'm a old timer. So I started my career in 1965. So you can imagine 66. So when most of you are not born, you see. So that is the time when we started. So what I propose to do is talk about how things have evolved over a period of time, in the last 6 decades, and how we have ended last year, and what is likely to be the future. Although I'm not a great predictor on this, I don't think any of us either, any one of us. And most important thing is the confusion and hype sort of that is created among most of us as youngsters. That's why we keep on changing the topic names and subject. Even curriculum also will change. See, that is the problem we are facing currently. And students especially are confused because what is there, what they should learn at this point of time, and also what is going to happen 10 years from now and so on. Nobody can predict, but at the same time, what we should learn finally, how to learn, rather than worrying about, you know, specific thing that we learn through courses. Okay, having said this, the topic I have chosen is evolution of artificial neural network architectures. And
please share your screen. Sir, please share your screen.
Beg your pardon?
Please share your screen, sir.
I can't hear.
Share your screen. Please share your screen.
Share your screen. It is already there.
No. Again, please share.
Can you help me how to do that?
Yeah, you just go to new share. On the control, you just click on share, new share. Zoom controls.
You're seeing?
Yes, sir. I changed.
Screen there? Can you see?
Yes, sir.
I'm not able to hear.
Yes, sir. I can see.
Can you see the screen? No.
Yes, sir. Yes.
Okay, fine. Anyway, although I have prepared a few slides, it is unlikely that we go through in that order, or maybe most of just for the outline I have given some slides. Otherwise, our discussion will be somewhat more, much more than what is available in the slides. Okay, so let us start now. You know, most of the subjects that we know, for example, in engineering, for example, take my field, for example, electrical engineering, and all this electrical engineering and the discipline of electrical engineering has started or surviving because there are certain basic principles or fundamental laws. For example, Coulomb's law or Maxwell's equations and so on and so forth. So the whole field is built on that. And this is true with almost every other classical engineering field, like, for example, mechanical, civil, and so on. But when you come to this topic of artificial intelligence, whatever it is, or learning, deep learning, whatever it is, there is no such basis. There are no fundamentals, you see, and that is where we are struggling, you see, and that is what I want to highlight here. So the terminologies could be quite confusing. So the motivation for my talk is to just focus on this learning and especially try to understand the distinction, to start with at least the distinction between human learning and the so-called machine learning. Even machine learning, I don't think any clear definition is evolved. Even human learning, of course, there is no definition, but we all learn, you see. So, but machine learning, we are talking about learning by a machine using what are called the models inspired by the structure of the biological neural network. That's why model, we are not talking about all machine learning here. We are talking about machine learning, that is learning in a machine through models that is inspired by biological neural network, and those models, we call them, as for want of a better name, artificial neural network models. So that is the focus here is the learning by machine using ANN models as opposed to human learning, for example. And everybody thinks that no, we are improving, we are almost matching human learning and so on. The answer is unfortunately no. In fact, the more we do, the less we are doing the right learning of a human being. And that's what I want to emphasize here. And to appreciate this point, we should understand, first of all, there are many issues in human learning. The most important one, my way of putting this is, humans learn through a process, whereas machines learn through product or example. It's very important to understand this distinction. The more you understand it, then you can understand the differences between these much better, rather than mixing up the concepts from one to the other. Again, I will repeat, humans learn through a process, whereas machines learn through examples or a product. You see, it's extremely important. Of course, what is the process and so on. For example, if we were fortunate to be all crossed the stage of learning, otherwise when we are kids, let us say about 4 years, 5 years and so on, you can see how we evolved, understood the concept of addition, for example. It's not that we are thrown hundreds of addition examples and asked us to learn. There was somebody like a teacher or a parent or a friend or somebody trying to explain what is addition, you see. And it is that process that is ingrained in our minds, and we learn the concept of addition. And while we learn the concept of addition and also apply it inadvertently in all, effortlessly in all cases, if somebody were to ask to explain what is the concept of addition and how we learned, I don't think any of us can explain at all. You see? And that is a human way of learning, and it remains so. And you keep this thought. There are many other examples I can give, but I think keep this thought in mind so that when you come to the topic of learning, especially machine learning and leading to deep learning and so on, you will appreciate what is it that we are doing, and most important is what is it that we are doing and we cannot do. You see, that's to appreciate. So the objective of my talk is focus on learning by machines through artificial neural network models, and I'll come to the details of this. But the ANN models, there are broadly, this will go through this talk. There are broadly two types of learning that takes place in an ANN model. You see? And one is what's called the discriminative learning, and the other is what's called the descriptive learning. And it is extremely important to understand the distinction between these two. We'll go through it several times in my talk. So the learning by ANN models, there are two broad categories. One is descriptive learning. That means, let us say, if you give characters A and B, and we can discriminate which is A and which is B. No matter you give varieties of A's and varieties of B's, we can discriminate between them. But that is one type of learning which is possible by what is called artificial neural network models. And another type of model is what is called the descriptive learning. What is descriptive learning? Suppose A and nothing else, let us say, maybe 2-3 examples of AI, several of them say. So what is it that you learn there? You learn how to describe AI. It's not the descriptive learning. It has nothing to do with the discriminative learning. In the first case, when you give A and B, it's a discriminative learning. That means how different B is from A. You don't worry about description of A and description of B or something, but you are worried about how different they are. Both these concepts are important. Why am I introducing that in the beginning of this talk itself? That is because the idea of deep learning came from that, and combination of descriptive and discriminative learning is deep learning. Deep learning that we use as of today is not deep learning at all. Please understand that. It is a wrong term that is in prevalence, and somehow we have to live with it. But when we live with it, at least we should know that it is the not right term that is used, because the deep learning is a combination of and discriminative learning. We'll go through it throughout this talk. And before we do any of this, I thought, let me give an introduction or a historical introduction to this ANN. That is, one second, I am trying to switch the slide. Yes. Anyway, this is the outline. Let us not too much worry about it, and let us go through this. This is a very important slide. Okay? All of us, so I am sure most of you may know, but I am going to highlight maybe some aspects which some of you or many of you may not know. You see, and notice that this is a history of ANN, artificial neural network. It was not called ANN probably in those days, but it all started. From what we know, of course, it has been there even before, from 1940s, what is called the Hebb's law, Hebb's learning law, and so on. You see, and that is, and before that, of course, there is also a proposal. There was also a proposal by Mikulowicz proposing a neuron model, biological neuron model, MP neuron model, and notice Mikulowicz learning law, Mikulowicz model, and Hebb's law. They are not together. They are on separate discoveries of propagation, because Mikulowicz neuron doesn't have any learning involved, whereas the Hebb's law is only for learning. How human beings learn through biological neurons and so on. I'm not going to elaborate on this. I just want to reel out how we started in 1940. It's a stock of human learning, biological neural network was there even before also, but it was not as formalized as it was from 1940s that was happening. What I want to focus on this evolution is very important. You should grasp, capture here. 1940s, as I told you, neurons and Hebb's law. I say that is starting to understand biological neuron and so on. In fact, Mikulowicz neurons are not used for learning or something like that. They were used to build Boolean logic circuits and so on and so forth. Now what happened is, in 1950s, which all of you know, the term AI, artificial intelligence, was coined by John McCarthy and others. And the artificial intelligence word was coined. Mainly, this is where a lot of confusion even today. This, in fact, we will elaborate this again toward the end. AI, what was thought of AI at that time has nothing to do with what we talk about AI today. The idea of AI, when they formulated in 1950 conference, that AI was meant to if we can describe the way humans learn and also human intelligence, then we can demonstrate it by simulating on a machine. You see, that was the idea of AI. That means it was more of understanding of human learning and human intelligence rather than worrying about whether you can implement on a machine or not. What it says is, since we know how to program a computer, if we know how can precisely the learning and intelligence of a human being, that can be simulated. That's all that they said. That was AI. Please underline these words, very important, because that concept has almost evaporated today. That's right. And then notice the way I have written here, I specifically, of course, there, but I want to. So, in 40s, neuron, biological neuron, and Hebb's learning. 50s, AI, artificial intelligence, because trying to understand, describe the human intelligence and learning and so on. 60s, it so happened, because AI was still.
Hello, sir.
Sir, audio is
Sir,
missing.
your audio is muted. Can you please unmute?
Done anything, but
Yeah. Yes, sir. Yes, sir.
how much I missed, I don't know how many people have missed, but anyway, I think as
Just now.
stop within few seconds, you either call me or give
Yes, sir. Yes, sir. Just few seconds only.
indication through video. Okay. All right. I was talking about 40s and 50s, AI, origin of AI in 50s, and then 60s. Of course, AI was symbolic when logic and so on was going on, but I think Perceptron model, and through Perceptron learning, you can demonstrate some features of pattern recognition. For example, handwritten characters can be automatically recognized by a perceptron model which was built at that time. And so, but then, in fact, if that had succeeded, we would not have the computer that we have today. Please note that. If that idea had succeeded, because there was euphoria around that time saying that, okay, perceptron model can solve pattern recognition problems and so on and so forth like human beings. And then if unfortunately or fortunately, whichever way you want to put it, because we should say fortunately, because it was Minsky and Papert who analyzed that very carefully, and in 68 they produced a book called Perceptron saying that this is not going to work. It is a highly constrained this one. There are a lot of issues there. I'm not going to discuss that. So, and everybody kind of chided Minsky for destroying or for killing the neural network field at the time, you see, because they produced that book saying that perceptron cannot do many tasks and so on. It has nothing to do with the human way of doing and things like that. And then you can just see why I put this slide again. So then there is again a dampening of this neural network business. And then AI started picking up again. So in the 70s, it was all again AI, and especially starting with what is called the search technique. And most important is heuristic search. They demonstrated on what is called the game playing situation. For example, chess and checkers and so on and so forth. And they demonstrated that not the brute force said, you map the problem, because game playing, especially chess and similar, are supposed to be intelligent tasks, and you can demonstrate the intelligence part of it on a machine. That's what they thought. And why they have chosen the game? Because it's possible to represent the positions of the board or whatever game, and also the legal operations on that. And where is the intelligence part coming here? Because if you put it as a brute force search and searching through all possibilities, there is no intelligence. The intelligent part is what is called the heuristic set. That is, among several billion operations available, options available at each stage, you only prune to a very small number. That's what a human being does, and that is what they made a machine also to do. And so it is that heuristic that you use is so-called intelligent part of it. And there was an euphoria in 70, and almost the whole of 70s is devoted to AI. And neural network work was going on in the background, but nobody talked about it anymore. And it was AI again, heuristic set. And again, at the end of the 70s, suddenly there was a dampening of AI completely. In fact, although there was an expert system, knowledge-based system, people were desperately looking for how to get out of this AI business in 70s. And so that is when in 80s, there was a breakthrough in terms of producing 2 volumes, what are called the PDP volumes, and produced by Rumal Halt and McClelland. They are MIT Press volume, And what do those volumes say? PDP means parallel and distributed processing volume. Everybody in the field of machine learning and neural network should know the existence of those volumes. In fact, better still if you at least browse through them, because they are about 2 volumes each of 1,000 pages. Because still better if you can read through some of them, because even after 40 years, they have shelf value and lasting value. And that is the one that triggered ANN. You see, that's why. So ANN was not there before. ANN was there in bits and pieces with a limited demos and so on. But it took up a big way. Why did it? Why did the ANN come in such a prominent way? Because not because ANN was useful, because they were fed up with AI. That was the point. You see, the so-called knowledge-based systems, expert systems, such technique, they didn't know what to do, where to go from there. You see, and so this ANN gave them a rescue. So everybody dumped whatever they were learning in AI and jumped to ANN. You see. And so, and notice this ANN, every time this transition from AI to ANN, neural networks and so on, but here, that's why the Rummelheld and McClelland, the authors of PDP volumes, they were very careful in not using the word neural network at all. For the simple reason that they know at that time itself that we cannot understand the biological neural network, period. So PDP volumes simply mean they are PDP models, parallel and distributed processing computing models, which demonstrated a few cognitive tasks, which are similar to, like, for example, human memory, how it works and things like that. And there are various other aspects, like, for example, how the knowledge is represented in a human being. And they were all demonstrated through what are called the small computational models called the PDP models and so on. But of course, engineers don't keep quiet, you see. So they immediately said, oh, we'll call it as ANN and so on. Instead of AI, now you call it ANN, artificial neural networks and so on. So there was an euphoria again, and that is when the ANN started. It was in 1986. Please note that before that there was nothing like ANN and solving problems with ANN and so on. It was more of intellectual curiosity, which they credit Marvin Minsky and Papert that they have destroyed the evolution of this AI in 1960s because their book on Perceptron. So now they revived this ANN. Why was it revived? We will show, because you remember in the beginning of my talk that there were no fundamental laws in AI, and some fundamental results came up in through the PDP volumes. That is the one that found the basis for ANN. You see, and that's what we are going to discuss for about 15 minutes, half an hour or so. The main topic of this, that is, so far I have discussed how we have reached the point of ANN. That means, what are the origin for ANN, artificial neural network models for solving problems. So solving problems. You see? And since they are inspired by the biological neural network model, the artificial neural network models are nothing but the inspired by this, our limited understanding of the structure and functioning of the biological neural network. You see, that's why it's called ANN. You see, and and it is supposed to perform what are called the pattern processing. Notice that human beings are known to do only pattern processing. They can never do data processing. You see, suppose you are giving 1,000 telephone numbers. Can you remember all of them? No, you cannot do that. Or if you are given large number of numbers to add or multiply, you cannot do that. You see, and whereas, you know, if you are given several names or cities names and so on, you can remember them. The reason is that you derive a pattern out of it and you link the patterns that are already available. So again, I don't want to go into details of that, but it is enough for us to remember that pattern processing is a human attribute, and the ANN models were developed for demonstration of pattern processing tasks. That is where ANN became very popular. And so noted that the ANNs are models, artificial neural network model, inspired by the structure and functioning of the biological neural network, not that they are simulating exactly that, but using some connections and some artificial neuron model and things like that. You see, and what is forgotten, I will elaborate a few things there. And of course, it ran for about 8 to 10 years, from about 86 to 95 or so. I think it was all ANN, everybody. In fact, everybody, whichever field they are working on, they dumped what they were doing, including civil engineers, total, what is it, sociology people, economic people, everybody, they thought ANN is the future kind of a thing. So everybody started looking at ANN and everybody started writing books. In fact, there are many books written by arts people, science people, engineers and philosophers and so on and so forth. So basically, please understand, I'm going to spend a little time on that. ANN models started in 1986 for addressing pattern recognition task, because pattern recognition, or in fact a more general term is pattern processing, is a human attribute. Notice that machines can never do pattern processing, period. You see? And only human beings can do pattern processing, and humans can never do the data processing. You see, just to pause and then give one example at least to say, what do you mean by this processing? Which for example, you are looking at my slide now, you see, and when you look at the slide, what is, somebody asks what is there in the slide, what will you say? You will say history of ANN. You will say, you will why like that, you will say. So notice that you don't say there are white pixels and then black pixels and then white pixels and so on and so forth. You see, very important to understand. So that means from the data you already captured a pattern of H, pattern of I, or in fact not even the pattern of that entire word itself. And that is what you are capturing and then articulating it or storing it or linking it with other information that you have and so on. So that is what I meant as a pattern processing. On the other hand, you put a camera and scan it and store it. What is it that you store? You store pixels. You store pixels, white pixels, black pixels, and so on and so forth. And then what is it that then you write a computational algorithm to find out if there is a pattern in it, and then what it is, and so on, character recognition. That's not there, not then built. Whereas here, without you are asking, you are able to recognize the pattern and so on. There are hundreds of examples like that can be given. One more very example which I want to give, because it poses a challenge since 1980s when I started teaching this course, even today, and I think it will last for a few more decades. The challenge is what is called the temporal pattern capturing ability of a human being. For example, you watch a TV, or you are now watching me, let us say, talking about it. What is it that you are seeing here? You are in a video. You are not seeing how many frames are moving per second, or you are not seeing how many pixels are there in each frame. You are automatically getting the video part of it, how my hand is moving and so on, and also the speech part of it and so on. So your ability to capture the temporal pattern without representing it in the form of a pixel, samples, frame, and so on, is the beauty of the human intelligence. It is the beauty of the human pattern processing ability, and there is not a trace of a machine. Machines can never, not only now, in the next foreseeable, at least not in my lifetime, you see, and it can never do also for any time, for the simple, the more you probe in, the less you will know about it. That is the beauty of the biological neural network, and can never be simulated in artificial neural. So just a small deviation to tell what is pattern processing and also the processing by a human being as opposed to a machine and so on. So then let us spend a few minutes, maybe almost about 15-20 minutes on this ANN basics. You need to understand these ANN basics because you will be surprised to know that currently the so-called deep learning, which I will discuss toward the end of my talk, have nothing to do with neural networks. Again, please note, I am very clear, I am emphatic, and And if anybody is thinking that it is because books write like this, experts like this, they are all wrong. You see? So that is where you need to understand what is neural network, what is artificial neural network, and why, so that you can appreciate that what we are talking about today or in the current AI or deep learning models and so on, that is not neural network at all. So what is this neural network here? So, and again, as I told you, these artificial neural networks are meant to perform what are called the pattern processing task. I think before I elaborate on that, I will take another slide for that. You can just see, I will quickly go through it and come back again. So the neural network models for pattern processing tasks was the hot topic in for about 8 to 10 years, from 1985, 86 to 1993. But slowly they realized that it is not possible. It is not possible to do more difficult tasks by ANN models. You see, they realized by middle of 1990. In the meantime, fortunately, the computing power was increasing enormously, and our data capturing ability also has increased enormously, data storage and so on. So that is when the machine learning simply means you have large amount of data, you want to find out whether there is any information or pattern or in the distribution of the data. Please underline the word distribution. If in fact, this is the question I ask to a lot of people, including experts, and especially when I interview candidates for faculty positions and so on. Not even one candidate who has, all of them had PhD in learning and teaching, gave correct answer. Not even one in the last, among about 50 to 100 people I met. That is because that was never highlighted. See, machine learning was simply meant to capture if there is any pattern in the underlying word distribution of the data or distribution of the features in the data. That is important. You see, if there is no distribution, if there are only random numbers, the data consists of only random number. No matter what machine learning algorithm you use, it can never find anything there. You see, so there must be a pattern not in the individual but in the distribution of that. So whole machine learning, if you want to summarize or crisply state what it is nothing but capturing the distribution of pattern in the distribution of the large amount of data that you have. And that is when the three tasks have emerged: supervised learning, unsupervised learning, and reinforcement learning. Notice, very important again to understand, these three tasks, I use the word tasks. These three tasks are some tasks. I have some data, input and output, I want, it becomes a supervised learning. If I have some data and I want to group or cluster them automatically, like k-nearest, that becomes k-nearest neighbor algorithm and so on, that becomes unsupervised. You can also go a little further and say, no, there is nothing like supervised and unsupervised. For example, when I am playing games or something, anything, of course, game is the illustration. When I play this, when I lose or win, I know I learn something. You see, that is the point. That is the reinforcement learning. That's why you can see all the chess grandmasters or chess players and so on, they have to keep on playing, whether they lose or win, because each time they learn. And that learning is to be called, that is called the reinforcement learning. So notice that these three tasks have emerged out of this machine learning of large amount of data, and in fact, that is the core of machine learning. Machine learning is nothing but a set of algorithms and a large amount of data which can be broadly categorized under the three such tasks and so on, and capture that through the distribution that you have and so on. That is all machine learning. Okay? And please note that, in fact, that's why machine learning existed much before many of these things that we talk about. You see, so and that became very prominent because you had machines and data available and so on. Notice again, I am emphasizing this table that I have written. So ANN during that period, that is roughly 1995, 94, 95 to when the machine learning started coming, ANN gone into the background. Very few people talked about ANN or artificial intelligence from 1995 to 2005 or 6. For those 10 years, or just blank. Very few, of course, a few people must be quietly working on it, but if you can't afford to talk in public because that is not a fashion anymore, you see. And in fact, you will not be, your application will not be shortlisted if you say that you are working in AI and ANN in those days, you see. That was because machine learning was at the top, you see. And then what happened? I want to summarize this and go back to my ANN again. So what happened after that? After that, again, later, that means around 2005, and why ANNs were given up in, somewhere around early 90s and so on, or mid 90s, because you didn't know how to develop an architecture for a given many pattern processing task that you perform. You didn't know how to perform, and everybody thought it was the limitation of the computing power. They never thought that it is limitation of your human thinking or human abilities. And once the computation power came, they dumped the field, the ANN model, and they went to about standard machine learning algorithms and so on. And suddenly what happened is, and so around toward the end of 2000, that in 2006 in particular started, suddenly there was a revival of this ANN concepts because the data became so huge, you can also build very large models and so on and so forth. That is when the concept of deep learning came. Actually, deep learning came not because of large amount of data, but by a very clever idea which Jeff Hinton had proposed in that. I will elaborate on that as we go along. And that is when the deep learning started. And around 2010 onwards, if you see, that is the 2010. And what happened is, even that deep learning concept was dumped. And then 2010-12 onwards, deep neural networks ideas came, and then the deep learning idea came, and then that's all. Even today we are thinking that is the field that we have to be in, but be careful because it may be dumped anytime in the very near future, you see. And I will tell you why, because I will briefly tell DNN has nothing to do with the neural network. Deep learning has nothing to do with learning. That is the problem, you see. And in fact, it has nothing to do with learning, nothing to do with the depth, you see, and depth of learning. That's what I will elaborate that as we go along. Please don't mistake me to say that what people, you should still use what people are, everybody is using and following, but you should have at the back of your mind a clear perspective of what if everybody is using, you can't use your own terminology, so you go ahead and use them, but you should understand the limitations of those terminologies, see, because most of them vanish and replaced by some other terminology. So I want all of you to just to keep this flow intact. In fact, see, most of you are professors and so on, so I cannot command you, but I can request you. I can request you to please write 3 to 5 pages on what we have discussed on this. You see, that write it on 3, 4, and then read it. You will get a clarity on our understanding of this. You see. And unless everything is together, you will not know. I have deliberately prepared to show how they're fluctuating between ANN, artificial intelligence, and finally we are thinking everything is AI and so on. And we will come to that toward the end of that. So let us now go back to 1980s artificial neural network models, and so let me see if I can. Okay. This is this slide is the most slide. Unfortunately, what happened is many of the current generation students and even faculty, I must say, I think those who are maybe in the age group of below 40 or whatever it is, and most of them have never paid attention to this, you see. And although why I said it before that they have gone through this, and so they have still at the back of their mind some appreciation for this, but current generation people may not have, but you will see the core of artificial neural networks and pattern recognition lies here, and it is our inability to deal with more sophisticated tasks related to this is what made us switch over to something else. You see, that's what we. So let us start. We'll spend about 10-15 minutes on this. You see, and the core of artificial neural network is what is called the model, artificial neuron, biological neuron model called the artificial neuron model. Very important, and that is also called the perceptron model. There are many models for that, and perceptron model is probably the most famous one. And notice that this is a computational model, highly simplified version of a biological neuron. Biological neuron, even a single neuron, its functionality, understanding. People have spent their lifetimes and got a couple of Nobel Prizes given, but still they don't understand. What to talk of the network of biological neuron. You see, so, but let us take only the simplified model of the biological neuron, what is called the artificial neuron. Artificial neuron has two components. I should have put some blah, but I'm sure most of you know. It has two components, just like the CPU of a computer. A perceptron has two components. One is what is called the weighted sum. The other one is what is called the output function. A weighted sum and output function, and that means large number of inputs are given, and for a neuron, let us say, and each of those inputs are weighted, and that weighted sum is what's called the activation value. And then this activation value, when it exceeds a threshold, it fires. If it doesn't exceed, it doesn't fire. You see, this firing and not firing is the main function of a biological neuron. And in fact, you will see the moment you dilute that functionality, the power of the biological neural network also comes down. You see, very few people understand this, unfortunately. And those who understand also, they want to hide it for the simple reason that you want to join the current euphoria that is there. But so the perceptron, that means weighted sum of all the inputs, and then that activation value, and the second part is the hard limiting threshold function. That means if the weighted sum, which is called the activation value, or in the case of biological term, called the membrane potential, if it exceeds a particular threshold, it is firing, and otherwise not firing. So one of the functionalities of a biological neuron is existence of in these two states broadly. That is firing, and there is nothing in between kind of thing. Of course, this is also an approximation, but it's a good approximation to that. And it's firing and non-firing. That means hard limiting threshold. And you can see, although I don't have time to discuss, and also it requires a little more mathematics to show that the moment you dilute that one, again, I want to call this model as an arithmetic and logic model. That is, the arithmetic part is the weighted sum of the input, and logical part is the hard limiting threshold. And both parts are extremely important, especially the logical part is important for the biological network or the human being to perform the way they are performed. In fact, the biological neurons are not endowed with the functionality of a firing and not firing, or if they are replaced by a sigmoid function or a linear function, I think they are as good as dead. You see, for the simple reason that it loses all ability of learning and knowledge, storage, everything. You see, intelligence and so on. The intelligence part is in that hard limiting function. You see, and so you can, and there are a number of theorems for that. And of course, as you can see, the current generation of people, they don't want theorem, they want only a Python program tool, that's all, so that they can run it with some data. But if you understand you will get disillusioned with what we are doing now, although it does good job on many tasks and so on. So perceptron, and another very important result there is, of course, there are many other interesting things which I don't have time to discuss, but perceptron model, what I described is only some part of it. The main part which Rosenblatt, Pabor, everybody has dropped it, but I am also dropping it. But anyway, just to trigger your this one, what I am missing here, or what I am not saying here, is the role of the association units which feed the input to the perceptron. That part I am not discussing at all. In fact, that takes a lot of time. So again, this is the perceptron model, and there is not just a perceptron model like this. There is also a learning, very beautiful. notice all of us miss the point that what is learning? A learning law is nothing but, you see, the moment you say a perceptron, and suppose you put the perceptrons in several layers, that means you have a number of perceptrons in one layer, and again another layer of perceptrons and so on, feeding one to the other. That is called a feed-forward architecture or a topology. And if you have some such thing, how do you adjust the weights for a given task, input-output task? That adjustment, there is no algorithm to do that. Whereas if it is only a single layer perceptron, with a number of perceptrons, that means input and output layer, then there is a learning law, a very famous learning law, which is called a perceptron learning law. Again, it may sound a little trivial and simple. No, it is very powerful learning law, but the simple reason that the moment you have a perceptron, notice that you end up in what is called a set of inequalities. What do you mean by that? Suppose you give in some inputs and those weights, weighted sum of that, those weights are the ones which you have to adjust for a given task and so on. And so the weights are there and weighted sum, and you are saying if it exceeds a threshold theta, fire. If it doesn't exceed, don't fire. Even 0 or plus 1, minus 1, any two states, it doesn't matter. So that greater than 1, threshold it is 1, less than it is 0. What does it mean? Can anybody see what it is? And if you have number of such perceptrons, you have so many inequalities. And what do you mean by solving a problem in a neural network, artificial neural network, this perceptron? That means find out those sets of weights which will satisfy all these inequalities. And you notice the beautiful, in fact, this aspect is almost forgotten in the current literature, but that is the power of a human learning. And so if you have a set of inequalities, you have to determine the weights which will satisfy all the inequalities, and you can't determine by any algorithm or logic. There is no computation here, so that is why you needed a learning. Learning means what? Yes, adjustment of the weights from the given input-output data. And this adjustment is done not randomly, but in a systematic way. Since there exists a systematic way of adjusting the weights of a perceptron network, that is why that learning law is called a perceptron learning law. The beauty of that is, that means notice again, not now, after another few years, this will come back. Because now it is all forgotten, because the whole human ability is in that inequality. And notice another very important, so if there may not exist a solution also. For example, if I collect, let us say, A, B, A, B, B like this as one group, another A, B, B, A, another group, let us say, and you say I call this as one class and the other one as another class. You can see this is not a classifiable problem. You can't solve this problem. You see? So perceptual learning, like if you start applying for this, it will never converge. It will never give you a set of weights, because you will get inequalities in such a way they contradict each other. For example, what do you mean by contradicting each other? Give me a number which is greater than 10 and less than 5. You see? Obviously you cannot. You see? So it is such inequalities you end up in the case of learning. And so that means if there exists a solution, for example, give me a number which is less than 10 and greater than 5. You can see there are infinite number of solutions. You see? And any solution is okay. That is exactly the core of the perceptron learning and perceptron network and biological learning. You see, and you can see, and of course, as a result of this, what happened is using this you can demonstrate what are called the pattern classification problem. What do you mean by pattern classification problem? Suppose, as I told you, if you have given large number of handwritten characters A's together, because I write A, you write A, somebody else write, all of the human being you show, all of them are A's, although no two are, you can't match them in a pixel by pixel form, but all of them see that they are A's. Likewise, you can give several number of B's, samples of B, and you want to design a network So that if somebody else, another person comes and writes a A, you should say that is A, not B, and so on. And that problem is what is called the pattern classification problem, and that is indeed solvable. That is indeed solvable by a perceptron network. You just see the beauty of the small things help a lot to understand what is not being done in the big things. You see? So this is what we call the pattern classification problem. And what happened is, as I told you, provided the pattern is classifiable, the classes are classifiable. And as I told you, if you give a random problem, it is not classifiable. But but there are very difficult problems where it is classifiable by human being, but a simple perceptron learning cannot be classified because the way you represent this problem into the system is such that it is not classifiable by a perceptron network using perceptron learning law. That means you cannot determine the weight systematically using perceptron. Then what do? What you do is you design what is called the multi-layer perceptron. That means not one layer, 2, 3, 4 layers, one output. So multi-layer perceptron with input and output dimensions are determined by the dimensions of the input-output vector. Then it is able to capture them, or it is able to classify them. But there is a catch here. Yes, it is able to get geometrically also argue and show that, but then what is the catch here? I don't know how to adjust weights anymore. Perceptron learning law is no more applicable if I have more than one layer. And that is when the breakthrough result came, what is called the backpropagation learning algorithm. In our backpropagation learning, the error from the output gets propagated back to an intermediate layer for you to adjust. But then what? There is a catch here. You cannot propagate if it is a perceptron unit. The unit has to be, that means you can't have an output which is firing, not firing. It should have a continuous function. The moment you have a continuous function, it is no more a neuron. Please note that. But so you have only you can say I am approximating a neuron, but that approximation you have already destroyed the power of the neural network, you see. And so, but of course you can see the operation successful. You are able to adjust the parameters and so on, but the patient dies. That means it is no more a neural network anymore, and not neural network. That's all. But again, even that limited way of looking at it helped to realize an approximate classification solution to approximate solution to a classification problem and so on. So backpropagation learning is the. You remember in the beginning I told you what is called the discriminative learning and the descriptive learning. And what this does is, when you say two classes you want to separate by using a training a network by means of a, this is a discriminative learning. A feed-forward neural network performs what is called the discriminative learning. That means you give several samples of A, several samples of B, several samples of C, and so on. Any number of classes like that, you can design a network multi-layer perceptron which can capture the pattern information that discriminates between these two. Notice I didn't say describes. In fact, none of these pattern classification, feed-forward neural network, multi-layer perceptron can never do description. It can only say how different you from the other person. Discrimination between these two. If you suppose some students of yours have come to your office, 3 or 4 of them and so on, your human mind is such that you quickly look at them, oh, one is taller than others, or one is this one is brighter than, like this, you start comparing like that, both physical and other mental attributes and so on, rather than worrying about, oh, is it full of 5 feet 4 inches, or is he wearing this shirt or pant, and you don't see that, you see. So your human mentality is to capture the discrimination among them. On the other hand, if only one student comes at every time, then you start capturing what is called the descriptive features of that person. So this feed-forward neural network unfortunately captures only discriminative properties. So that's why it's called the discriminative learning. But that's not enough. Human being does both discriminative and descriptive, and that is why other topology of neural network is what called the feedback neural network. A feedback neural network where every neuron output is connected to every other neuron. You see, and then you become what is called it is a feedback neural network, and with a certain constraints on the weight. That means for a n-unit feedback network there are unsquared weights, but put some constraints on that. The beauty of that is it can indeed capture the pattern information that is available in a given single sample. Then you can give only one example of A, it can capture the pattern information. On the other hand, suppose you give a very random sketch kind of a thing, just a zigzag thing, then it cannot capture anything because there is no pattern information there. You see? So the beautiful part is, that's why I said feedback neural networks capture what is called pattern information in a single or a fewer number of samples, not discriminative. So since it captured the pattern information in each of these samples, that's why it is becoming what is called the descriptive. You can also generate the pattern if you want to. You see, so that is why it is called the pattern storage task. A pattern storage task. So one example of that is, for example, I can collect 100 faces here, passport size photographs of 100 people, faces and so on. I can store and represent each one of them by some number of pixels, let us say 64 by 64 pixels. And I don't need a second sample. These samples are enough for me to store the pattern information available in each one of them. What do you mean by I have stored? That means if any of them later comes, notice that I may still have 64 by 64 pixels of his face, but it won't be exactly same as what I had taken earlier. But still the beauty of that is this particular network captures that pattern information and recalls what you have stored. So that is the beauty of this pattern storage task by feedback neural network. So this feedback neural network is nothing but a description. It captures the description of and there is a beautiful learning law called the Boltzmann learning law. That means a Boltzmann machine is nothing but a feedback neural network with constraints and with certain features and so on. That's why it is called a Boltzmann learning law, a Boltzmann machine. And the beautiful part is there exists a learning law which can adjust the weights of the feedback network so that it captures this pattern information in all the input data that you have. That means you can store 100 faces or 500 faces and so on. And you can still recall them even if you give a partial input to the system, partial information. That is called the, notice why I am emphasizing all these concepts have vanished now, you see. But but if you go to the whether they are useful or not, I don't know. But the fact is, these are much more closer to the biological network than functioning than what we are seeing today. And now what happened is, in fact, if you get, although we don't have time to discuss this, but the point here is the feedback neural, both these, especially feedback neural network, is based on a very solid mathematical foundation. So the theory of that is highly sophisticated. But then what happened? Why is that the Boltzmann learning law is not become very popular? It's very powerful. It's not popular because the computing power, I'm talking about in late 80s and early 90s, the computing power that was required, none of the machines existing at that time was, in fact, I remember in Japan, several what do you call that, supercomputers were running parallelly to get one small result after a week or 10 days. You see? And so that is why, in fact, that is one dampening effect on neural network, and the kind of neural networks, slowly the interest was fading away in the mid-90s, see, because of the Boltzmann learning law, which was not, but it is very powerful. It is the way human being does many things. And unfortunately, you cannot implement on a machine, or you cannot make a machine learn this. You see, even simple tasks like storing a face of human being, or to talk of more sophisticated tasks which we are all used to, like for example, temporal patterns like videos that we see on a TV and so on. So that is when the field came to a standstill between 1995 and 2005. But as I told you, not that people are keeping quiet on that. Both AI and ANN went to the background, and machine learning took the center stage. You see, and that's what happened. It's all that is when the support vector machine, decision trees, all these things have come in there, and they have nothing to do with the ANN, and they have nothing to do with artificial intelligence. You see, they are simply machine learning algorithms. You see, please note, machine learning even today, although people say it is related to AI, it has zero relation to AI. And so it is simply algorithms for which you have specific supervised learning, unsupervised learning, reinforcement learning. How do you realize that? What are the algorithms to do that? That's what the machine learning. And you can, you have enough data and machine power to do this. That is where. But then what happened is, conceptually, if you see, there is very little in the machine learning for us to understand, except the fact that you have a large amount of data. You are worried about the distribution of that data and the features in the, whether the distribution and any particular feature. If the distribution is all random, then it is useless again. Fortunately, every physical system, every practical data has some implicit features in that, implicit distributions in that. That's what you want to capture by means of machine learning algorithm. So it was riding high for 10 years. It was, was there any question? Interruption? Okay, I will go ahead. So it was in 2006, very important year, 2006, the Boltzmann machine that was proposed in 80s suddenly got revived by the same people who introduced that. The only thing is, they made this Boltzmann machine slightly simpler, that means approximated a little bit, so that the learning law can be implemented more in realistic computation. So computing power has increased, and you have reduced the complexity, approximated Boltzmann learning law, so that it can be implemented. And that is where, and what do you mean by implementing? That means you can now derive a description by using a reasonable computing power. And that's why the Boltzmann machine, that is called the restricted Boltzmann machine. It was a restricted Boltzmann machine, which is nothing but a feedback network, but a feedback network, a earlier feedback network, when I said, let us say, the feedback network here, or even Boltzmann machine, it is fully connected. There are n units, all units are connected to every unit is connected to every other unit. Whereas a restricted Boltzmann machine, you have two layers of neuron, and there is no connection between the units within the layer, but one layer, entire units are, each unit is fed to each of the units in the other layer, and vice versa. So that means if there are n units in the first layer and m units in the second layer, there are n into m connections, and those are the way that is called the restricted Boltzmann machine. And although it doesn't perform, it doesn't have the functionality of the original Boltzmann machine, but it has some semblance of that, but reduces the complexity several orders of magnitude. You see? And that helped in kind of a coming up with, that is the concept of deep learning. Please understand, if any time, of course, if the other person who is testing you or interviewing you, if he doesn't have the knowledge, you are helpless, of course. But if he knows, if you say, this is the meaning of the deep learning, that is where the descriptive and the discriminative learnings are combined. That is, this restricted Boltzmann machine, you train two layers, keep it, and then add one more layer, train between those, and again add one more, and then thus create several layers of a network. And then that multi-layer network, you can use it for in two ways. One is, if you use that can be called a, it can be used for a classification like a multi-layer perceptron with the weights that are trained by the restricted Boltzmann machine idea as an initial weight, and that becomes a classifier. On the other hand, if the last layer of that, if you make it as a feedback network, all others are feed forward, that can be used for generating a pattern. So let us not too much. So these are called the deep networks. One is what is called the deep belief network. Another is what is called the deep, neural network, kind of deep neural networks, you see, which is for a classifier. That is the concept of deep learning. Again, I will repeat. Concept of deep learning is a combination of descriptive and discriminative learning. Both are used, and that's what human being does. You see? The beautiful part here is that that's what we do without subconsciously, and you are able to show it, develop it. That is where the deep learning idea came. But then what happened is, the machines are getting, increasing power. In fact, what was available on a huge computing centers now in 60, 70, now you have 10 times or 100 times more powerful on a simple mobile, you see. So that is the kind of computing power, and of course storage. You can imagine how much. So because of that, they said, why are you doing all of this? This is not required, and just to put everything in a one single, what I call the deep neural network, and you don't have to do even this initial training by a restricted Boltzmann machine and so on. That is when the current concept of deep neural networks has come. The deep neural networks currently used has not using any of those ideas of descriptive learning or discriminative learning or something, or they don't use the restricted Boltzmann machine idea, which was the one used for understanding deep learning, and now it is simply a deep neural network. It's simply a large number of layers and with millions of parameters and so on, and a huge amount of data running to, if it is videos, Facebook talks about billion videos or billion videos and so on. I mean, that is how we got into madness of this data and computing power and so on. So beginning 2010 onward, that is what's called the deep neural networks and deep learning. You see? So this is the, now what we will do. So this is the background that so what we discussed in the last 15-20 minutes is artificial neural networks, its origin and what it was meant for. And notice in those days, that means when 86 to 96, the idea was you had a task in mind and you wanted to build an architecture. That means you want to build an artificial neural network model which involves both the topology as well as the learning algorithm to realize the task. Please note again, you have to emphasize this point that you had a task in hand, a pattern recognition task in hand, and you develop an architecture for that. You see, and that was the focus in the beginning of the neural network, and that is where you can see the architectures that they were evolving. There are how many? Hundreds. How many learning labs were there? Thousands of learning labs. Because for every architecture you need a few of them I am throwing here just for a, so there is what's called the competitive learning neural network architecture. It was meant for pattern clustering, for example. Self-organized mind map architecture. It was meant for self-organization. Human beings are so good at self-organization and we take it for granted, but it's a huge, there is a machine algorithm which can do that. Self-organizing map network and so on. And there was there are many architectures. I listed a few to tell you that somebody talked about the temporal pattern, for example. When I'm talking about the speed, there is a pattern, the sequence of sounds that you produce. So how do you capture this? That is, there was an avalanche architecture that was developed. And then suppose you write characters, especially in cursive script or hand printed here. You write several ways, size-wise, tilt-wise, and some additional things you add. This is called a pattern variability. In all of that, you can still see A. And so there was a neocognitron architecture which was evolved at that time. And there was also stability plasticity. Human beings are so good at this. That means, what do you mean by stability and plasticity? It is in learning. For example, today in the any of us, let us say, in the previous hour you attended a course on data structures, let us say, and now you are attending a class on neural network, and maybe after some time you will attend a class on economics or something. So what does it mean? Same biological network, same weights are adjusted, and so what you learned in data structure you cannot forget when you are listening to neural network, and what you understood in neural network you cannot forget when you are doing. So you have to read it. See, same neuron, same weights, but they get adjusted, readjusted to the retaining the old one. That is called the stability. Plasticity means bringing in the new pattern that you have got, keep retaining the old one. This is what beautiful human way of looking at it. This is called the stability plasticity feature of a human ability. And there were architectures almost for 10 years. There are books on it. There are 1,000-page books on ART, written by Chen and several others as well. On ART means Adaptive Resonance Theory Architecture. So that was architecture developed to realize the task of stability and plasticity. You see, that's what I'm saying. So they were focused more. Stability, plasticity is the problem, and ART is the architecture that has evolved out of it. And likewise, convolutional neural networks. You see, it was developed almost in 40 years ago. You see, and what does it mean? It is mainly meant for image classification and in architecture. Likewise, recurrent neural networks and so on, for temporal pattern sequences and so on. There are many other. So what it means is, in those days, you think of a problem, a pattern recognition problem, and design an architecture which can realize this. Notice again, you define a problem, see how you can develop that means designing an architecture is a problem solution. Designing means both topology as well as the learning law for that, you see, for the given problem and also the data associated with the problem. Notice that was the focus at that time. These are the architectures that were developed and so on. And then what happened? This was during 86 to 96. And as I told you, around the next 10 years it was machine learning. And then again, 2006 onwards, again, Boltzmann machine I already mentioned, restricted Boltzmann machine I mentioned already, and deep belief network arising out of that. And then DNN and DBM. DBM means deep Boltzmann machine. DNN means deep neural networks. And so all the deep things were using the idea of deepness in the restricted Boltzmann machine related. Please understand it. So that was the growth of deep evolving architecture between 2006 to up to 2010, 11 and so on and so forth. You see, and people were thrilled with all of the development. You see, they are able to understand what was going on and they are very happy. But of course, all that became irrelevant from 2012 onwards. Why? Because then they said, dump all the theories, dump all this learning law, dump all of this. Simply use a large network. A large network means several layers of this. How many layers? Maybe hundreds of them. How many neuron weights? Maybe millions of them. And so large number of layers and consisting of large number of weights and so on. And large amount of training is required to adjust that. And you need a criterion to adjust it. You see, and that was all that is done. You see, from then, of course, they showed a few important interesting results like image classification. It's several order of magnitude better than what it was before. That's all. You see, and that is where the current idea of deep neural networks. So the current deep neural networks, starting from 2012, has nothing to do with deep neural network talk before, 5 years before that. You see, important to understand. And the current deep neural network is nothing but a large number of layers and with hidden units. And of course, the units are something like a, they are not really perceptron units, but they are simply artificial neurons with appropriate slight changes are made for the activation function and so on and so forth. Notice this is nothing to do with neural networks. Although they call it a neural network, there is no human biological network has no layers at all, first of all. You see? So no feed forward layer. And none of the neurons in deep neural networks none of them are neurons. You see? They have no feature of neuron at all. And so, but still, and what is it, you may ask? What is it? It is the beauty of that is, it is a computational model. It is a nonlinear computational model. And since it is nonlinear, you need a criterion to adjust and iterative solutions and so on. That's exactly what it does. It has nothing to do with neural networks. Please understand, this is very important. In fact, you can see, I will show you a few definitions. After listening to it, you will see most of the definitions are unfortunately wrong. What is being quoted now. But if you are a teacher and you are teaching this, you can't escape, you have to use those definitions. You see? So this is where our dilemma is at this point of time. But anyway, you have to go ahead and use it because that is what books, paper, and other material shows, and general scientific community uses that. But otherwise, you can see. So anyway, so the deep neural networks are nothing but a large number of layers of non-linear computation model consisting of large number of layers and the adjustment of the weights to realize a given task and given in terms of input output is what's called the deep learning. A deep learning, the deep word is because you have a large number of layers. That way, the deep network they call it, and deep learning. Otherwise, first of all, it is not even learning. It is simply an adjustment of notice. Why did I say it is not learning? Please go back. That's why I spent a few minutes when I talked about perceptron. Perceptron, that is learning. That means you have a set of inequalities and you have to satisfy the inequality, weights to satisfy the inequalities. You see, parameters to satisfy the inequality. Here there are no inequalities anymore. It is simply a complex function. You have to iteratively find the best solution and so on by iteratively adjusting it. So it has nothing to do with that kind of a learning. So there are no inequalities here to learn. You see? And so ultimately, if you take, unfortunately what happens is you can change the machine, but you cannot change the human being. You cannot destroy or modify his biological neurons to operate like your deep neural network or something like that, you see. So, and that being the case, the power of this is different from the power of that. They are complementary, but not competitive. And so these are some of the things that have evolved using the deep neural network. Deep learning, as I told you, is simply an algorithm to adjust the weights of this complex. When I say complex, it's not really complex. It is complex in terms of large number of parameters to adjust. That is why it is complex. And the adjustment here, now if it is a machine is there, not only instead of 10 items, can go to 100 items. Instead of 1,000 numbers, it can deal with 1 million numbers. What is the big deal? There is nothing there at all, you see. So, but it is complex if you want to quote in terms of numbers, because in 88 to 98, if you talk about a neural network, I think if anything exceeds 1,000 weights, already it is very difficult to handle. But now, million weights is simply a small number, you see. That is the contrast and so on. And so these are some of this idea of a deep neural network and deep learning to adjust the weight. And you have all this. But before I come to this, you have to understand that deep learning is simply an algorithm for a deep neural network. It is not even a task. When I said not even a task like the machine learning task, like supervised learning, unsupervised learning, reinforcement learning, they are tasks. They are not associated with any architecture. Whereas deep learning is a task, it is not a task, it is an algorithm associated with deep neural network. It is very, very important for at least as teachers and as researchers for us to understand, although we still use the terminology and the way others talk because we have to be in the same wavelength as others, whether that is correct or not. But whereas we should keep at the back of our mind that deep learning is not a task. It is simply an algorithm. And whereas other learning tasks, supervised, unsupervised, reinforcement, they never are linked with any architecture. You see, they are simply tasks. You can realize it by several means. You see, that is where so many machine learning algorithms have come. Please, and those tasks still exist. Whereas deep learning vanishes at the moment deep neural network vanishes. And another important thing in this, maybe I will come to that in the next slide. But before that, let me just throw a few terms here. Just as I threw some names earlier, convolutional neural network, autoencoder, recurrent neural networks, LSTM, long short-term memory, generative adversarial network. All students, researchers, especially young researchers, people like me don't worry about it. That's all. Anyway, I don't have to learn anything more. But these youngsters have a problem because they think, oh, these are all great things. Don't waste your time. If you want to learn them, just set apart 2-3 days and you will learn learn 99% of it. There's nothing to learn in it. There's no concept to learn there. See, please note. I know all of you are excellent programmer and Python programmer. Then it is all the more easy. Within 2 hours, you start code for this. And maybe if you are still interested in learning, you take another 2 days to learn what it is doing. And that's all that is there. I'm not exaggerating. That's a fact. You see? And so these are all the architectures that have evolved around DNN. You may say, why did not many, about half a dozen varieties like this? You can see, because depending on the problem that you have on hand, for example, if it is a static classification problem, or if you have a distribution capturing problem, or if you have a temporal pattern information problem, or if you have something else which is, kind of a implementable temporal pattern like LSTM and so on. These are all some of the, so these are limited number of architectures to deal with certain situations. Otherwise, all of them apply similar learning laws. You see, and all of them apply similar law. Maybe 1 or 2 criteria, objective functions may change, but otherwise they'll apply. So these are, so the architectures are fixed. Please note that they have nothing to do with the problem anymore. You see, and I will come back to that again. So let's the next slide. You see, and applications of this. Anyway, again, as a student, as a researcher, you are almost, kind of confused in the first place. And then you think that you are missing something, others are running faster and so on. Don't worry, let them run far. You see, you will catch with them or they will come back because it's a circle. They will come back to you before you try to read them anyway. So these are all applications, natural language processing, machine translation, text generation. Not that they are not important, but they are realizable with these models and they are not that great. After all, only thing that is difficult for us, especially in India, to do it is you don't have that machine power and you don't have that data. And in fact, you don't have the data and machine power. It is foolish for us to think of addressing these problems. There are enough number of challenging problems that one can address in a related area. But thinking, how can you compete with a Facebook which trains a model with 10 billion videos and so on? I was told that they are willing to give you a few million videos if you want to train and so on. I mean, you are enriching their idea rather than coming up with anything new of your own. You see? And it is none of these models, none of these tasks can be done with your limited laboratory computer or even a few GPUs are not enough. I was told, I heard the talk by Facebook, this was about 3 years ago. They were using, I think, 1 billion videos and 400 to 500 GPUs of high-end GPUs, and to get the result in a few hours or something like that. And what do you mean by that? We have to get our result only after when we are gone. It will not come in without limited come. So we should also understand what tasks we should tackle. You can never compete with them, and it's not worth competing. You see, please note that. These are all, there are same natural language processing can be done in many different ways. You are not even looking at it. Same machine translation can be done in many different ways. You see, notice that the task, it was not that they thought about the task and then tried to design. There was a structure and they thought of this application. Please note that. You see. So I think this is very important to understand. There are many more now. You can list about a few thousand applications. And so now I will come to the most important thing. Can I take another 10 minutes? What is it? Josna?
Yes, sir. You can proceed. No problem.
Okay, fine. So I am coming to the last part of my talk. That is discussion of artificial intelligence, machine learning, and deep learning. All of us, including me, are so confused with this. And so this diagram, all of you must be seeing. You see, machine learning is a subset of AI, deep learning is a subset of machine learning. This is all wrong. Unfortunately, it's all wrong. But still, if you have to teach a course, you have to go with this because that is where reported in the books and this one and so on. It has machine learning has very little to do with AI. Deep learning has very little to do with machine learning. There may be a small overlapping, subset kind of a thing. But otherwise, you can't say that machine learning is fully part of AI and deep learning, because first thing is we don't know what is AI. You see, we don't know how to define AI, and we are already calling machine learning as a subset of AI. You see, and deep learning, as I explained already, if you carefully look at it, it has very little to do with machine learning. For example, it has nothing to do with the kind of a task like you do the decision, what is it, decision trees or regression, for example. All of these are machine learning. They're not AI tasks. Regression is not an AI task. You see? And so you please understand this is very important. But having said this, be careful. You have to follow this because industry bombards you with all of this. And some of us academics are brainwashed by them. You see? So we are not allowed to think independently in a scientific manner and come up with this. So we have to learn to live with this. Otherwise, as I told you, AI, we still don't know what we should call AI. Machine learning has a clear objectives which has been there for the past 25, 30 years. And it is, and DL is, we know DNN, training algorithm for a DNN and so on. And now you will see, just to see some definitions I copied just now. And so you can see, deep learning is a function of something, is a AI function, simulates human brain and so on, processing data for detecting object. I mean, this is all wrong. As a scientist, I get irritated with this kind of an answer. You see, I think because you can see deep learning has nothing to do with human brain. Has nothing to do with the human way of learning. And another next line you can see deep learning is a subset of machine learning in artificial intelligence. I don't know who. And if you carefully look at they are good topics. I'm not belittling them at all. All I'm trying to say is you try which doesn't exist is what confuses. You see, one good is bliss. If you don't know anything, you can get the books and so on and say this is what it is and so on. But if you start thinking, applying your own mind on this, you get confused. And if you are a teacher, you are in big trouble. Big problem. But otherwise, if you are an active teacher and you have to teach it, you have to teach something which is against your conscience, if you understand the subject. As I told you, if you don't understand, as I told you, ignorance is bliss. You say that person has said so, you are saying it, fine. But the moment you understand, you are in trouble, you see. And so deep learning. And machine learning is the study of computer algorithms that improves automatically through experience. This is almost an afterthought of all of this. In machine learning algorithms, they never use this word, you see. I think this is where we are struggling actually. That's why as teachers especially, you have a big problem. And the research supervisor, you have a big problem. That's why keep all of this, follow the crowd. Only thing I'm suggesting here is, but keep it at the, when you discuss with your student, no harm, saying that, okay, this is what it is, this is what we understand, this is what we don't understand. Like this is how you have to do rather than, because that will open up many, many more interesting problems rather than simply applying another Python code and so on, using another Python code for another data and saying that, somebody comes up with, what is that, how long a person can live, a deep learning model to tell how long a person can live. What that nonsensical, these are all, I think, stupid tasks should not be even attempted. You see, it doesn't make any sense at all. You see, and just because you have data and input and output and so on, you started doing the. But as an exercise, please don't mix up with the concept and exercise. As an exercise, you are welcome to do it. But you can't generalize this. So I just thought I will alert you on this. Again, don't get me wrong in this saying that I am condemning this. No. All I am trying to say here is there are methods, very good methods, very successful, and you should teach them, develop them, use them, and make money out of them if you can and so on. And on the other hand, but don't call them as this and this and it is simulating human task and it is replacing human beings. It can never replace human beings. Forget it. You see, it can. So this is the very important concept. That means this and the previous one and the previous one. I think as teachers, especially since I know, as I was told by Josna, that I'm addressing mostly teachers of Vignan College. I think this is the most Vignan part of it. You will get, if you understand, appreciate it. Not that you can be an expert here, but you should appreciate as a teacher, if something works, I have no interest in that. We need to know why it is working and why it is not working. That is the goal of a teacher or a chair or an academician in particular. For business people, it is just the opposite, of course. Okay, so even if that something is working partially, they will have to show in color slides and so on. They did this and so on. You know, so I sell the product and then forget about it, close the shop. See, so but that is not the case here. And also, don't believe all these things. AI can replace everything. AI can make your jobs unless you are trained in. If you are trained, it's good to know. Definitely, there's no question about it. And it is good to invest time and to know what it is and so on. But don't think that if you don't do this, you will not survive or you cannot get a job and so on. All that is not. These are all hypes, and I don't believe, and none of you also should believe. You see, and you should draw your own conclusions rather than going by somebody else's statement, including mine, of course. So I would like to now conclude this whole thing by the following: that is, what we have talked about is learning by neural networks, artificial neural networks. And as I told you, learning initially was to realize a particular task by developing a artificial neural network model to realize the task and learning on that. You see, on the other hand, the current learning, so-called deep learning, is for deep neural networks and so on. And whatever you call, none of the old ones or even current ones have very little to do with human learning. We still are left with the void that we don't understand how humans learn. You see? And any number of studies have been made by all kinds, sociologists, psychologists, philosophers, because what to talk of scientists and so on. And the worst part is computer scientists, because they think that they can produce an algorithm immediately for learning and so on. Be careful, we don't understand what learning is. Why I am highlighting this part here is, there is plenty of scope to do that. You see, that's what I'm saying. If you carefully apply your mind and so on, plenty of scope, any number of good research papers can be done and so on. So, and just to highlight a few, not completely, a few of the human learning tasks, you see, as opposed to machine learning tasks. Notice I'm very careful throughout. You can see I said deep learning by ANN, machine learning by ANN. I am not using the deep learning by any other methods. Machine learning by other methods. You see, so I am using only for so these are all human learning. Just the contrast is easier. You see, because ANN is supposed to be a structure of artificial neurons and so on. So human learning, it's of course this particular slide, especially even the second line that you see, this alone is a one semester course. I can just take about 40 lectures on this, and there is so much to understand. So we are finishing in 40 seconds or maybe 2 minutes or something. Human learning is pattern driven, and humans process only pattern processing through the biological neural network, and you can only recall patterns. You see, you cannot recall the data. And I have human doing what is called there's a beautiful thing called selective attention. Last 1.5 hours you are listening to me, and you think that you have heard what I am speaking. Notice that you have not even taken even 20% of the sound that I have uttered. You see, that means you selected what you want, and remaining you didn't even bother to listen. You see, that is called the selective attention mechanism of human being, and that each person does it in his or her own way, and that is how you capture the information. On the other hand, if unfortunately we are endowed with this, if we are endowed with an ability to capture every sound that I utter, just, then take it from me that you don't understand even a bit of what I utter. See? You will not understand anything at all if you capture every part of it. You can create hundreds of examples for this. I'm just giving you a selective attention mechanism. We don't know how to realize it by a machine. I don't think we will ever know that also. And I already mentioned about what we call the processing and representation. I don't want to elaborate on that. And the most important thing here is, that is why you can see, people can say that, oh, I can replace teachers with online lectures and online lectures with slides with something else and so on. Like they know. In a class, a teacher produces for a concept a pattern in a high dimensional space. What is that high dimension? It's millions of dimensions. And it is that high dimensional pattern, the teacher credibility or ability lies in producing the type pattern in high dimension, which only students can absorb. Human being can absorb. A machine can never absorb that pattern. So this, to appreciate this or highlight this, I need several hours. But the only thing I can say is humans produce or capture patterns only in high dimension and not in low dimension. And that's why the role of a teacher in a class, that's why if you start using too many slides, let's say 100 slides, 200 slides for 1 hour lecture and so on, keep on flipping them, let's say you are already projected that information onto your low dimension and students don't get anything at all. See? On the other hand, you take one slide and explain it for 2 hours, then you are producing a pattern in a high dimension. See? I mean, to understand this, it takes some time. Need a lot of illustrations to give, but I don't have time to do that. And most important, all of you know already, I mentioned human learning based on parallel and distributed processing. It's not same as the parallel processing and distributed processing in a computer. It's together. That's why the PDP volumes have come and so on. And there are several other attributes of human learning, and which poses challenge, say for us, and this can keep all of us as academic busy forever, for any number of years and so on, to understand what this is. And then, of course, if somehow partial understanding, you can realize it by a machine. On the other hand, machine learning by artificial neural network models, mostly data driven, and the tasks are like classification, regression, and data compression. Most machine learning, that is, I did tell in the beginning, it is what is called the distribution of the data, probability data. So the distribution, the data is in high dimension. There will not be any distribution to capture. Can you guess why? It is called the crux of dimensionality. Because the amount of data that you need will grow in exponential or double exponential and so on as the dimensionality increases. So if you have a high dimension, the amount of data that you need to capture will be several orders of magnitude which you will not have at all. But for human beings, there's no problem at all. So in order for you to have the distribution in the first place, you need to reduce the data and reduce the dimension of the data. And unfortunate thing is, in that reduction of the dimension of the data, you have destroyed the problem already. See? The problem is in the links in the high dimension, and by removing the links, you have reduced the, and hence you destroyed the information itself. So it is almost like operation successful, patient dies, that's all. This is exactly what happens in this case. And this is very important to understand, in the machine learning. And of course, it is mostly distribution, low dimension. And also machines learn only from examples. As I told you already. Learning from, that's why you need large number of data, input, output, and so on. And then this example is for this example is for this and so on, only that you give and so on. Whereas for a human being, for example, when you are teaching a child, let us say, how to write character A or B or something, you don't simply write A and ask that child to learn. You will say, you have to hold the hand and say, put this line like this, and then A like this, and then like this. You have to explain that several times, several days, by giving other, and write B and say, this is not A and so on. So that process is ingrained into them. See, that is how you learn, process, whereas in the case of machine, you simply give those examples. See? So it's a very fundamental difference, not that they are contradictory, they are complementary. You need both human learning as well as machine learning to do their respective tasks, and together they are very powerful. But saying one is replacement of the other is somehow it is unscientific, although we use that unscientific also. So to conclude my talk, the last two lines are very important. From 86 to 96 roughly, of course, don't quote my dates exactly. See, there could be a few years this side, that side. In 86 to 96, it was architectures were evolving around applications. Please note again, architectures evolving around applications. That means stability, plasticity, pattern variability, temporal pattern. You have a problem, application in mind, and you need an architecture to develop. That was the now 2006 onwards, especially 2012 onwards, till now, and maybe for a few more years, it was applications evolving around architecture. You have CNN and the convolutional neural network, deep learning. That's hundreds of applications you bring in, throw it into that, and say you have done a deep neural network, and so on and so on. You never bothered about what the architecture for that particular problem. You have some fiction of it as an architecture. You simply throw the applications into that. Whichever application is useful for you, you have only offered as an architecture to play with, and that's all. And you can see as you probe more and more into the gap never gets narrowed down, it gets widened as you go along. Okay, so to summarize or to the whole thing, what we discussed here is learning is a human trait, and learning by artificial neural network is originally meant to simulate the process through the structure and functioning of the biological neural network to see whether you can do a limited extent the pattern processing task that human being does. And that is how learning has evolved in artificial neural network. And slowly the machine power, other things have, artificial neural networks are forgotten and pattern recognition tasks are forgotten, everything is forgotten. We have a few architectures and huge computing power, huge data and so on. And we are showing successful application. Applications are infinite, there's no doubt about it, you see. And so we are we have to do those applications around the architecture, but you can't claim or you can't say that they are simulation of intelligence or they are anything close to intelligence. None of them are intelligent tasks. I think I will stop with this. Thank you for your attention. I'll be happy to take some questions, and only thing is how that happens, Jyotsna has to decide.
Yes, sir. So they can unmute themselves and they can ask the questions.
Actually, Jyotsna, I am not able to get your voice. Your voice is breaking. In fact, even I don't know why. In the beginning it was good, but in between also you spoke something.
Is it fine for now?
I can hear the sound, but not the message. Something is. Can you hear me clearly?
Yeah. Yes, sir.
But
your voice is very clear.
The opposite is not correct. True. I am not able to hear, but anyway, try or make an effort. Maybe what I suggest is you reduce the volume and keep the mic close to your mouth. Let me see if that works. I'm not 100% sure about it. Reduce the volume and keep the mic close to your mouth.
Yes. Hello?
Yeah.
Am I audible?
Hello. You are audible. Yes, go ahead.
Hello.
So now the participants, you can raise your questions if you have any.
Hello.
Hello? Sir, please.
Yes. Yes, ma'am.
Yes, sir.
Ma'am, I'm Ravi Prasad. I'm ex-employee of Vignan University. I just wanted to have a small clarification from Yegana Narayana sir. So first of all, I want to thank Yegana sir for giving this kind of motivational, this kind of knowledgeable task for knowledge for us. And basically, I just wanted to know for my problem, what is the architecture that is suitable?
First of all, your question is if I repeat verbatim, what is my problem, what architecture is suitable for my problem? Is that what you're asking?
Exactly, sir.
I mean, there itself, the solution lies. If you know the architecture, the problem is solved. The
Yes,
rest
sir.
of it is only a programmer or a technician job.
Yes, sir. Because the talk was very interesting. Like you have given a brief introduction on what is CNN, what is RNN, what is ANN. That is all fine. That is all okay. But I want to understand what exactly if I have set of features, and if I have the outcomes. If I already have some set of features and I already have a set of outcomes, what architecture should I apply in this deep learning? I just wanted to know.
No, well, see, that answer nobody can give. What people are doing currently is you keep on trying different with a limited knowledge. He has applied this, so let me also apply this like this. And wherever it works, you take it, and all others you hide. See, in all of this, it is only the failure part nobody quotes. You see,
Okay, sir.
only. So, your question is very correct, and there is no unique answer for this. You see, and
Maybe if I will ask my problem, will that be suitable for you to suggest?
I cannot suggest a solution. I can only discuss your problem in detail, which may trigger a solution for you.
Okay, sir. Should I go ahead? I will take 2 minutes.
Beg your pardon?
Should I go ahead? It will take 2 minutes.
Okay.
So basically, I'm working on non-verbal clues. I'm working on non-verbal clues. I'm trying to extract facial landmarks and eye gaze movements and head pose movements and facial action units.
I think now I understand what you are saying. Any of these networks with you have to keep trying different iterations and so on, they will work satisfactorily. You see, any deep neural network architecture will do. You see?
Okay, sir. Thank you.
See, that's what everybody is doing, maybe including my own students. But so now I understand what you are talking about. Yes, you have a clear input and output what you want, then any of these models will work. The only thing is, because if you had done earlier a few things, you will get a few hints on layers or what to do, how to make the parameter, that kind of a thing. Or a few trial failures and so on and so forth. It is mostly trial and error. Please note that. And I am 99% correct in that statement.
Okay. Okay.
Okay.
Okay. Thank you, sir.
Yeah.
Yeah. Now, if any others have questions, they can raise. So, from the participants, third is ready to take questions. So please unmute before you ask your question. From the participants.
No, they can, if they have a problem, time to formulate, they can send me an email also.
Yeah, we'll share the email to the WhatsApp group. If there are no questions, then we can stop the session. So then start the closing.
Okay, sure. Shall we close it?
Few minutes, sir. Few more minutes.
Madam?
Yes, sir, please. Sir. Sir, now we have our Dean R&D with us. He wants to speak a few words. Sir, please.
Good evening, sir.
Good evening.
How are you, sir?
Oh, fine.
Yeah, actually, sir, based on the instruction of our honorable chairman, sir, we introduced few subjects in our EEE curriculum, sir, electrical and electronics engineering curriculum, like machine learning, Python program with Java, deep learning, and all.
Okay.
My question is whether our EEE students are able to learn all these languages within a span of 2 years.
Anybody can learn. I think why EEE, I think even a 10th standard fellow can learn. No problem at all.
No problem.
Don't worry about it because there's not any deep concepts to learn. It is only just a question of like any other programming language. So I don't think there is any problem at all.
If they learn, sir, will any company can observe them because they are also
that is the wrong question to ask. Because I don't know what companies you are talking about.
Software companies, sir.
It also asks a similar thing, then it is a different matter. But if other side companies ask me to come and interview them, they'll be in trouble. You see. So what I mean by that is they need to understand the basics. And these are all, otherwise what they are doing only is an example or illustration. You see. And they know what it is and what are the plus points, what are the minus points. It is their analysis, ability to explain that analysis is what normally should fit them a job rather than what type of thing that they know. Even if they know one language less or one tool less or one subject less, doesn't make any difference at all.
Okay.
You see, what is important is their ability to explain, that is their understanding. That is where as teachers, we have a bigger role to play. You see.
Okay, sir. Thank you, sir. Thank you.
Any other question? So unfortunately, I could not give any introduction of sir. So actually, at the age of at the age of 76, so he is still giving this kind of wonderful lectures. So we are really thankful to you, sir. So thanks for accepting our invitation and thank you for giving a wonderful lecture. So and it's kind of, you have cleared so many myths related to the neural network concepts and especially the deep learning and the deep neural networks. Am I audible, sir?
Audible, but your voice is breaking. That's what okay, go ahead and speak. Anyways.
Yes, sir. So we are really thankful for the wonderful talk, sir. So good things always come to an end very sooner. So now closing of the session. So on behalf of the organizing committee, I thank all the participants for joining this webinar. I hope this webinar served its purpose. So by giving a detailed discussion of the evolution of the artificial neural networks, sir has given very elaborated details of different neural network architectures and what are the means. Yes, sir, please. Hello? Anybody is having any question? So hello?
Yeah. Hello. Yeah.
Sir?
Madam, this is Nageshwar Rao.
Yes, sir, please proceed.
How would we find more research topics in neural networks, sir?
Oh, you said how would you find more research topics in neural networks? Is that the question?
Sir, sorry. Actually, I am I want to pursue PhD in neural networks. So that's why I'm searching now the related topics, sir.
Okay.
Yeah, that's why I am asking you.
I don't think, you see, neural networks is a tool only. It is not really a subject. You should link it to your domain, you see.
Okay.
Then lot more things can be asked, you know. You should. It's a good idea to think of applying neural network models and so on, but for what problem? You see, that is important.
Okay.
Domain and domain knowledge is very, very useful, important.
Because normally, sir, in review papers, we read so many. It is used applicable in medical applications.
You see, those are all most of them are hand waving, you know. don't give too much of importance to you. Of course, you just read the title and stop it there, that's all. Unless not much is coming out, most of the, some good review papers are there, I'm not saying all, but most of the papers are not worth reading, you see.
Okay.
Most papers these days are only for writing, not for reading.
Okay, sir.
So don't worry, don't get too much worried about such thing. And keep a domain knowledge and see what problems are there in that domain, and see whether these ideas, principles, at least some of them can be used for that application.
Okay.
You want to solve a problem rather than a tool. See?
Okay, sir. Thank you, sir.
That in my
okay, sir. Thank you, sir.
Okay. Thank you.
Hello.
Hello.
Madam, you completed?
Yes, sir, we completed. Yeah, so kind of we need to thank sir.
Yeah, thank you very much, sir, for coming.
Can you please stop?
For giving a wonderful talk, and most of our faculty members, I'm sure that they had learned some, valuable, aspects from your talk. And we are, on behalf of Vigyan's team to the university, we are very much grateful to you, sir, for and also giving an opportunity for all of us to listen to your talk. Though I was there in IIT, but I never got an opportunity to attend any one of your classes. But this is the opportunity which I got to listen to your.
Your voice is very low, sir.
Yeah.
Sir, voice not audible, sir. What
Your
you are
voice
telling?
is very low, sir.
This is hello.
Not audible.
Yes, sir. Not audible, sir.
Now.
Yeah. Now also
yes,
very
now?
less
I think
voice.
My I'm using actually set it of this quality, so I can't do anything at this point.
No, I can hear. I can get it.
Yes, sir. Now it's okay, sir.
Okay. So thank you very much, sir.
No, it's very kind of you.
Yeah.
Thank you all. I hope my only request to all of you is those who are prime in these areas and so on, you write about 5 or 10 pages on what you heard. That is the best way to realize whether you understood anything or not in your own words. You see, that's what is important. Okay, all the best, and
Thank you, sir.
Okay.
Thank you very much.
So let me take a minute and thank the dignitaries. So I would like to extend my special thanks to Professor Yegana Narayana for giving very detailed discussion on various artificial neural network architectures. So we are extremely thankful to our chairman, Dr. Yegana, who always motivates us to organize these kinds of events very frequently. I thank Dr. M.Y.S. Prasad Garu, Honorable Vice Chancellor, Dr. Raghunathan, Rector, Registrar, for providing enough support in organizing this event. And I thank our beloved HOD of the department, Dr. D. Venkateslu, for extending his wonderful support. And I thank all my faculty colleagues who are actively involved in organizing this event. Once again, I thank all the participants for attending this webinar. So, and at the end of the session, we'll share a link, and so that will help us to improve. And whoever fills that form, so they only will be getting the certificates. So thank you. I thank one and all. So thank you, sir. Thank you once again.
Thank you. Okay. Thank you. Bye.
Thank you, sir.